Okay, good morning, everybody. Before we get started, just a couple of things here. Looks like I'm going to be gone all of this week. So just a few things here. If you need to take the test that we took last week, mostly because you were in the play, um, let me know still. I'll probably have you take it with somebody else, either during one of your open hours or before school, whatever kind of works for them. If you're thinking about retaking that test, we're just going to put that on hold and do that next week, just because it's not going to happen this week, probably. So for today, um, yeah, for today, what we're going to talk about here is the unit circle. We've got day 3, which is introducing what a radian is and just the beginnings of how we work with those. Um, at this point, we're just going to kind of see how this goes. I know on the schedule it says that there's, the quiz over the stuff is next Tuesday. We'll play that one by ear. If that ends up getting pushed back, not a big deal at all. So our goals for today, we're going to talk about what a radian is and why we like them in math. There's a reason that, once you get into fields like calculus, it's pretty much exclusively radians. You'll see a mix of both next year and in pre-calculus, but eventually it's going all radians because we like them a lot better in math. And then the main thing is being able to convert between the two when you see one, being able to talk about the other one. So the first question is, well, if we're so concerned about getting rid of degrees, what is a degree? And more importantly, why are there 360 of them to make a full circle? So there's basically 3 reasons, and 2 of them are kind of similar anyway. But the first reason is going to be when this whole idea of a degree came up, a lot of the math was being done in Babylon at the time, and they used what we call a sexagesimal system. That means base 60. So they actually counted using the knuckles on one hand to keep track of like one thing. And if you count the knuckles on your one hand, just the fingers, 3 knuckles on each finger, 4 fingers makes 12. You can hold up, once you get to 12 on one hand, you hold up a finger on the other hand. 12 times 5 is 360. 12 times 5 is 60. So you get a base 60 system that you can count on your hands. And then the reason that 360 ended up being chosen is because of something a lot like this. You remember when we constructed things like equilateral triangles and hexagons, we use circles. This idea of we can divide a full circle into 6 equilateral triangles, and then each of those triangles into 60 pieces gives us 360 degrees. Second reason, and a lot of you have kind of brought this one up already, is that there are around 360 days in a year. And of course, people knew that it wasn't exactly 360, but what a lot of times what they did was they divided those up into 12 months of 30 days each, which then ended up with 5 extra days to throw into either leap years or celebrations or things like that. But 360 days in a year made sense to keep 1 degree per day of revolution around the sun. And probably the reason that you will most like to use degrees is because 360 has a lot of factors. A lot of things divide evenly into 360. You can divide 360 by 2, by 3, by 4, by 5, by 6. Not 7, but you can divide it by 8 and 9 and 10. Not 11, but 12 works. 15 works. Does 16 work? 16 should work, doesn't it? 16, I'm putting a question mark on. 18 works. And then you've got all the pairs. So, 2 times 180, 3 times 120, 4 times 90. What is 5? 18? No. 72. It's 72. 8 times 45. 9 would be, 40? 10 is 36. 12 times 30. 15 times, what's 15? I don't know. 18 times 20, and then you've kind of repeated them all. Why did I not put 6? 6 is 60. I know 15 works, but I don't remember what it goes into. Don't remember about 16. But, oh wait, I have a calculator. 360 divided by 15. It's 24. And then we'll see if 16 works. It does not. Okay, so you can see 360 has a lot of factors, which means it's really easy to do things like, think back to the test we took where we had an octagon and you had to split it up into triangles to find the area. Well, 360 divided by 8 meant each one was 45. You had nice numbers to divide 360 by. So all of this is just to kind of say that there's a lot of real good reasons that 360 degrees was chosen, but none of them have really anything to do with the circle itself. In the sense of the circle, it is a pretty random choice for convenience more than anything. And what this does is it makes it a little bit hard to see some of the connections that have to do with the circle because the numbers just don't really mean a whole lot in relation to the circle. Radians do, and you're going to see that in just a second here. Now, the downside of that, because the radians are not going to have some of those benefits of 360, mainly the factors thing. So it's not as easy to figure out, what's a sixth of a circle in radians. It's not going to be as nice of a number, but you'll see how we deal with that, and it's not the end of the world. So let's go ahead and take a look at what is a radian. You're just going to have to let it play. I don't know why I didn't start at the beginning. There we go. Okay, so what we're going to do here, we're going to take a radius, make a circle out of it. So that red line is the radius of the circle. And what makes a radian is when we take that radius and we lay it along the circumference of the circle. That arc that gets created, that angle that intercepts that arc, that angle is defined to be 1 radian. And so if we take that 1 radian and spin it around the circle, you're going to notice something here. We know the circumference of a circle is 2 pi times the radius of the circle. Well, the radius of the circle is 1 radian, and so the full circle is going to be 2 pi radians in angle measure. We're talking about the angle going around here. So this angle is 2 pi radians because the circumference of the circle is 2 pi radii, radiuses. That's the big connection that we have between the circle itself and the radian as an angle measure. It's not a random division of the circle. It is based on a fundamental property of the circle, the relationship between the radius and the circumference, which we call pi. Now, the downside of that is going to be because that pi is in there, when we write radian measures as decimals, your calculator spits out a radian measure, it's always going to be an infinitely non-repeating decimal. It is never going to be a nice number. And the reason, what we do with that is we don't write radians as decimals. Every time we deal with a radian measure, it is going to be written as a fraction in terms of pi. And so what you can think of here is, the animation here is about to get back to the point where it says, okay, the half circle is pi radians. And so this is 2/3 of that half circle, like right about there. That's 2 pi over 3 radians. Not as nice to deal with, but if we can stick to these fractions of pi, it's not terrible. And once you get used to it, it's not that bad. And you will see these a ton. You're going to spend so much time with these next year and in the year after that you're just going to get real used to these, to the point where you'll almost have most of them memorized. So, big summary here. 1 radian is the angle formed by laying the radius of the circle along its circumference. So when you take that circle and you lay a radius, 1 radius, that angle that it formed is 1 radian. Okay. So because of this, the full circle is 2 pi radians. Be careful there. It's not 2. It's 2 pi radians because 2 pi r is a circumference. So 2 pi radians is the angle to get around the whole thing. Circumference around the outside, 2 pi radians around the angle. And so we can write some equivalencies here. 2 pi radians is equal to 365 degrees. Or if we want to simplify it, pi radians, 1 pi radian, is 180 degrees. And so when we're converting these, we're going to use conversion factors. Now, if you haven't used conversion factors to convert units before, whether it's just like from feet to meters or something like that, this is probably one of the most common ways you're going to see these written. The big key here with conversion factors is that the top and bottom of the conversion factor have to be the same. So, wow, I messed that up entirely. Those aren't even right. So we're going to fix those. And they're wrong on the whole slide. That's what's even worse. Let's see. Can we fix them real quick? Okay, so I think I got it here fixed up for us. So first one we're going to do is converting from degrees into radians. And so what we've got here on these is our conversion factors. And on a conversion factor, the top and the bottom have to be equal to each other. And what that means is because they're equal to each other, this whole conversion factor is equal to 1. And you're going to see why that's important. So when we're converting from, for example, degrees, what we want to do is we're going to place the conversion factor with the degrees in the bottom. So we'll put pi radians on top. We'll put 180 degrees on the bottom. And the reason we do that is because these are fractions now, and we can simplify between them. So we can go in and we can say, okay, well, the degrees in the top and the degrees in the bottom are going to cancel out, which is great. That's exactly what we want. We can also, at this point, simplify a little bit more. If we can see something that we can go into both of these, 45 and 180, we can simplify those. So, for example, you might notice that, 9 goes into both of these. And so I could say, okay, well, let's simplify out a 9. 45 divided by 9 is going to be 5. And 180 divided by 9 is going to be 20. You say, okay, 5 and 20. I can simplify that even further. 5 goes into both of those. So I can take out 5 from there. I can take out 5 from there. And now, since I'm just multiplying straight across, remember, this is just equal to 1. So I can multiply these, not changing the actual value. So 1 times pi radians is pi. 1 times 4 is over 4. And so I get pi over 4. And now I'm in radians. The degrees symbol canceled out. Don't forget the negative sign. That's important. That was negative 45 degrees. And we're always going to leave these in terms of pi as a simplified fraction. One thing you might want to know here, if you go over to something like Desmos, you can get Desmos to simplify these for you. There you go, 1/4. Now it won't work if you put the pi in there, right? It can't handle the pi, but it can simplify the numbers for you. But next year you will be expected to do this without a calculator, so it would be a good idea to practice that. So same kind of thing going on here. I'm going to go ahead and grab, the whole point of this was to be able to just drag these down. And I'm going to multiply by this conversion factor. So because I'm multiplying, the units that I want in the top and the units I don't want in the bottom are going to cancel each other out. And now I can go ahead and start simplifying these fractions. Right off the bat, I see, well, both of these end in a 0. So I can divide them by 10, divide them by 10. Now I've got 15 over 18. And 15 and 18, 3 goes into both of those. So I can divide by 3, I get 5. Divide by 3, I get 6. Nothing goes into 5 and 6, so I can multiply straight across. 5 times pi is 5 pi. 1 times 6 is 6. And so I have 5 pi over 6 radians as my final answer. And so every time you're converting into radians, it is always going to be some sort of a fraction in terms of pi. Unless it is exactly 1 pi or 2 pi. It'll always be some sort of a fraction of pi. Now, when we go to convert back from radians to degrees, we are going to want to do the other unit conversion, or the other conversion ratio, the one with the radians in the bottom. And the reason we're picking the radians in the bottom this time is because we want those radians to cancel out. Radians in the top with radians in the bottom cancels. Also, you'll notice the pi and the pi cancel out. And so I've got now left over 4/3 times 180. And this is the point where before I multiply the 4 times 180, I want to see what simplifies. And I see, well, 3 and 180, or 3 and really 18 is what I'm seeing here. I can divide them both by 3. 180 divided by 3, well, 18 divided by 3 is 6, so 180 divided by 3 is 60, and 3 divided by 3 is 1. So now I've simplified everything. I can't simplify anymore. 4 times 60 is 240. Well, 1 times everything cancels out there, so it's just 1, 240 degrees. Okay, let's do another one down here. This time we've got negative 3 pi over 2 radians. So I'm going to go up, grab my conversion factor. You'll see here, every single time we're converting into degrees, the radians will cancel out and the pi's will cancel out. Then I can go through and look at what simplifies. You don't have anything to simplify this 3 with because all that stuff canceled out. But 2 and 180 simplify to 1 and 90. And then I can just go, okay, well, 3 times 90 is 270. 3 times 9 is 27, but 3 times 90 is 270. Don't forget the negative sign and the degree sign. So 3 pi over 2 radians is negative 270 degrees. Okay, the last thing we're going to do here is try to use some of our special right triangles to find sine, cosines, and tangents. So the way this works, we're going to take the time to actually sketch these out. This is one of the things that you're actually going to be doing on this quiz. Sketch the angle, find the reference angle to the angle given. Select which triangle to use. You're either going to have a 30, a 60, or a 45, 45. You're going to find the sine, cosine, or tangent of the reference angle because you'll be able to have the sides there. Make sure you're being careful with the signs, positive or negative. Okay, so let's go ahead and take a look at this one. So first things first, it says 315 degrees. So we want to figure out where that is. You can see we've drawn a picture here. 315 degrees is almost to 360. So I'm going to take 360 minus 315, and I get 45. That is my reference angle. So I'm going to go ahead and label my sides as a 45, 45, 90. I've drawn that triangle in. I know that the sides of a 45, 45, 90 are 1, 1, and root 2, where we've put x, x, and x root 2. One thing I'm going to do differently from the way this did it is I'm going to go ahead and include that negative sign right there because that was down. That's negative. It just makes it easier for me. So if I want to find the sine, cosine, and tangent, I just look at this. Sine of my angle is the opposite over the hypotenuse, negative 1 over root 2. Now, if you remember, I don't want to leave that root 2 in the bottom, so I multiply by root 2 over root 2, and I get a negative root 2. So negative 1 times root 2 is negative root 2. Root 2 times root 2 is 2, and so that's my sine of theta. My cosine of theta, my adjacent is 1, my hypotenuse is root 2, so I get 1 over root 2. I'm going to do the exact same thing here. So it was root 2. Multiply by root 2 over root 2. So I get root 2 over 2. There's my cosine of theta. Then my tangent of theta. Opposite is negative 1. Adjacent is 1. And negative 1 divided by 1 is just negative 1. There's my tangent of theta. Now, if you go ahead and just take the opportunity right away when you draw the picture to label the sides that go down as negative or the sides that go to the left as negative, you don't even have to do that last step. I think that's kind of silly. Label the sides first and then just do it with the negative signs already in there. It makes it so much easier. So just as a quick reminder here, you've got your special right triangles. When we talked about them originally, we used x's. When we do them with the unit circle, we just make the x 1 every time. So 1, 1, and root 2, 1, root 3, and just 2. So that makes it a little bit easier. So instead of having all that, you just have 1, 1, and root 2, and 1, 2, and root 3, with this being the small angle, and these two being equal. 45, 45, 30, 60, and 90. So make sure you're always going back when you draw those reference angles, always going back to the x-axis no matter what. If you're in this quadrant over here, like let's say you have 150 degrees, your reference angle is 30, you draw it back to there. So then we have 1, 2, root 3, but the root 3 is negative because it goes to the left. That's the kind of thing you're going to be doing on all of these. So give those a try. I'll have a different video probably of somebody else talking about this tomorrow. Not tomorrow, but Wednesday. And we'll go from there.